Okay, so this is a jumping ring exhibit. So just to give you a demo, when you press this button, the ring is going to go up. And that happens because pressing this ring puts current in these wires which go all the way through here. And that's going to induce a magnetic field, and we know that's true because of Faraday's law. So it's gonna, if you follow these wires, it's gonna put a magnetic field up. And then there's going to be current also induced into the ring because of changing EMF by Faraday's law, and that's gonna then cause a magnetic field surrounding it, and then these two magnetic fields, one in the wire, one in the ring, are going to repel each other, and this repelling force, since this can't move, is going to force this ring to go up. So just to see another example of that, now that you have the context. Yeah. So if we imagine that this is our tube with the wire inside, and then down here is our button, what happens is when we press the button, we're closing the switch. And closing the switch, since there's a voltage difference here, delta V, it causes current to flow through the circuit, because it's a complete circuit. It goes through the copper wire and then goes down. So because there's current flowing within the copper wire, we know that current induces a magnetic field. And we know that because, for one way we know this at least, is because of Ampere's law, where the closed loop integral of B dot dl equals mu naught I. So B field, we're getting current. Okay, so we know that's true, but then how does that cause the ring to move if we have our ring here? Why is it going up? Well, it's going up because now we have a magnetic field, so we have B, let's call it B1, I don't know. So this is because of the current flowing through these copper wires. Now, we know that Faraday's law, because there's strengthening magnetic fields here, it's going to cause, what is it going to cause? Well, it's going to cause an EMF, and that's because equals negative dB dt A, and then also cosine theta, but that's going to be I'll just put cosine theta, but we can assume that theta is going to be constant. Okay, so then if we divide this by R, so whatever resistance we have, we're going to get the current that is induced, and that's going to be induced in this ring. So we have now current in this ring, which is going to induce more B fields, but this time these B fields, B2, are going to be in the opposite direction. So they're going to oppose B1, and that is obviously going to push this ring up, and that's why when you close the switch, you get current going through these wires, which induces a B field, B1, which changing magnetic fields induces a current in the copper ring, which then current induces another B field in the opposite direction, so that's why. Okay, so right now, the spring right here is in its equilibrium position. Now we can store potential energy in here when we pull this back. Now, if we put the ball here, and we release this, when this comes in contact with the ball, the spring is going to convert the potential energy in the spring into kinetic energy in the ball, and it's going to go back here and open it. But to make it up to it, it's going to need some amount of gravitational potential energy, which it will get from mgh is the amount we're going to get. So you'd think that's how much we need to pull back the ball, but it's actually not true, because there's also going to be, if that happens, it'd go up and go just fine until it got here, but then it'll fall down. There's energy to complete the loop. So we need enough energy to satisfy Newton's law for centripetal acceleration, which is the force of the centripetal acceleration is going to be equal to mv squared over r. So when we do all of that, we figure out that this actually has an equivalent energy requirement of 5 over 2 of the radius of this loop, and then we can convert that into the potential energy for the spring, which is 1/2 kx squared, to figure out how far back we need to pull it for this to successfully go around the loop. So this exhibit right here, basically explaining how it works. So this exhibit right here, so what happens is we have this spring, so it's going to have some spring constant K, and then we have this ball of mass M, and we have to pull it back some distance, delta X. And the first part is we're trying to make it through this, or allow it to go around this ring of radius R. So what we see here is how much potential energy is stored in the spring. So that is going to be 1/2 K delta X squared. So when it is at this point, we can figure out how much energy it needs to make it all the way through here. So just when it's at this point, it's going to have how much potential energy, well, equals just by the conservation of energy, so delta equals 0. That's what we're doing here. mg times 2 r, because we're at twice the radius when we're here. Well, we can't just have this. If we just have this, it's not going to make it the entire way, because it's going to go all the way up here, and it's going to fall right down. This is a pretty common mistake. Because up here, if we draw a force diagram at the top, what we have is, okay, if we imagine that this is the minimum amount of energy necessary, then up here, it will just be getting by. So there'll be no normal force acting, pushing this in any direction. So we're just going to have our gravitational component, because there's no normal forces here, because it's just enough energy to make it through. So we then set up our equation for centrifugal acceleration. So mg is the force, equals mv squared over r. Cancel this. What's the minimum velocity we need is then square root, or just, we don't even need to find that, we just know that gr equals v squared. So then, this also has, so if it has some velocity v when it's up here, necessary, found from this, to complete the loop, then we can find the kx as this part 1. But if we wanted to actually make it the entire loop, we need 1/2 k delta x squared to equal mgr plus 1/2 mgr, because that's 1/2 mv squared, but the v squared is gr. So then we have equals, again, this is 2r here, messed that up, 5/2 mgr. So yeah, then we can solve for delta x if we know k.
This is a handheld generator, so what happens here is we have two permanent magnets here, and when I turn this, that causes a change in EMF. Now this changing EMF is going to induce a current in these coils, which is going to flow through here and complete the circuit, allowing the resistors, which in this case are LEDs, to turn on. So when I crank this, the current is going through because of the changing EMF, which turns on the lights.
What I've misspoke in the video, it's not a changing EMF per se as much as it is a changing magnetic flux. So this is just Faraday's law kind of summarized. It also equals a changing B field, because magnetic flux is just the B field times the area. Add a cosine theta in there because they're not they're all a dot product or whatever. So basically what this is saying is we have our magnets here, and we also have this other magnet in the center. So we have all of these B fields around each individual magnet. But what happens is when we put in work, so we put in work to spin this, which is with its own magnetic fields, we get changing magnetic fields. So the direction changing, which then is going to induce current, because a changing magnetic field is changing magnetic flux, so it's changing magnetic flux. And there's coils wrapped around these, right? So they are able to carry charge and move charge. They're conductors. So then when we have this changing flux, we then induce an EMF. And because EMF, if we divide it by resistance, is going to equal current, then we have a current flowing through this. And because this is connected to a circuit with some resistors, and these resistors are the light bulbs, that means that since this circuit is already complete, I don't know exactly how it is completed, but the current is going to be able to flow through from the changing magnetic fluxes,